Hello number theorists, and welcome back to our course about number theory and cryptography. We've seen in our previous lecture how to solve equations of the form ax is congruent to a certain b modulo a certain integer n. In this lecture we would like to investigate systems of linear congruences and see how to solve them. As a starter, we would like to solve the system x is congruent to 3 modulo 5 and x is congruent to 2 modulo 7. This means that we're looking for the numbers x which leave a remainder 3 modulo 5 and leave a remainder 2 modulo 7. From here, actually, one can deduce that x must be of the form 3 plus 5k for a certain integer k, and from the second equation one deduces that x must be of the form 2 plus 7 a certain another integer k prime. Now the thing is, not all the x's of the form 2 plus 7k prime leave a remainder 3 modulo 5. For instance, if k prime is equal to 0, we have x is equal to 2, and 2 is not congruent to 3 modulo 5, obviously. Now if you take 2 plus 7, which means k prime here is equal to 1, we get 9, and 9 leaves 4 as a remainder modulo 5 and not 3, okay? It's the same thing for 3 plus 5k. Not all the integers of the form 3 plus 5k leave a remainder equals to 2 modulo 7. For instance, if you take k equals to 1, we find that x is equal to 8, and 8 does not leave a remainder equal to 2 modulo 7. So what we're looking for is all the integers x, a single formula that we can deduce from both of these that will generate all the x's verifying this system here, meaning verifying both of the equations at the same time. To do so, we will proceed with two different methods, and the first one is that we can subtract both of these equations here to get that 3 plus 5k minus 2 minus 7k prime is equal to 0, and this is because x minus x is equal to 0. From this, we can see that k and k prime are a solution to the equation 5k minus 7k prime is equal to minus 1. And this means by multiplying both sides by minus 1 that 7k prime minus 5k is equal to 1, and said in other terms, the couple minus k and k prime is an integral point on the line of equation 5u plus 7v is equal to 1. So if you can solve this equation here, which we know how to solve, we would get solutions of our system here. Let me write down things properly. We know that minus k prime is an integral point on the line 5u plus 7v is equal to 1. And to find all these solutions of this equation, we will apply the Euclidean logarithm, and we know that 7 is equal to 5 times 1 plus 2, and that 5 is equal to 2 times 2 plus 1, and that finally 2 is equal to 1 times 2 plus 0, which means that the GCD obviously of 7 and 5 is equal to 1, and from this we deduce that 1 can be written as 5 minus 2 times 2, which is equal to 5 minus 2 times 7 minus 5 times 1, and this is equal to 5 times 3 minus 2 times 7. Now from here we know that 3 minus 2 is an integral point on the line of equation 5u plus 7v equals to 1, and from which one can deduce that 5 times u minus 3 plus 7 times v plus 2 is equal to 0. This means actually that 5 must divide v plus 2 by the Gaussian lemma, which means that v is of the form minus 2 plus 5t for a certain integer t. This means actually that k prime is equal to minus 2 plus 5t, and from here we can deduce that x is equal to 2 plus 7k prime, which means 2 plus 7 times minus 2 plus 5t, and this gives 2 minus 14, which is minus 12, plus 35 times t, meaning that x must be congruent to minus 12 modulo 35, which is the same thing as 35 minus 12 modulo 35, and this gives 23 modulo 35. Now, is 23 modulo 35 a solution to this, to our system? Actually, yes, because 23 is congruent to 3 modulo 5, and 23 is also congruent to 2 modulo 5, and this works actually for every x, which is congruent to 23 modulo 35. Bingo. Let me write things down here to understand what I was saying. I was saying that x is congruent to 23 modulo 35, and this is also also congruent to 23 modulo 5, and 23 modulo 5 is actually the same thing as 3 modulo 5, which means that if x is congruent to 23 modulo 35, then x must verify this equation here. Same thing, x is congruent to 23 modulo 35, which means that x is also congruent to 23 modulo 7, and 23 modulo 7 is the same thing as 2 modulo 7, and this is the required result for the second equation that we have here. What we proved here is that all the solutions are of this form here, 23 modulo 35. Bingo. So this way of solving our system of equations worked very well, but actually for systems of more than two equations, it is not very efficient. What we're going to do next is to solve the same system using a different method derived from the famous theorem, the Chinese remainder theorem. So let me remind you that we would like to solve x is congruent to 3 modulo 5, and this same x is congruent to 2 modulo 7. Instead of solving this system, we are going to solve two systems of simpler equations actually. The first one is x is congruent to 1 modulo 5, x is congruent to 0 modulo 7, and the second one will be x is congruent to 0 modulo 5, and x is congruent to 1 modulo 7. Actually, I'll denote this x1 here and this x2 here in order to deduce from this the solutions to our initial system. So I pretend that if you're able to solve both these systems, we're going to be able to solve this one. This is because actually, if we have x1 congruent to 1 modulo 5 and congruent to 0 modulo 7, and x2 congruent to 0 modulo 5 and congruent to 1 modulo 7, then the number x, which is congruent to this 3 here, so 3 times x1 plus the 2 which is here, 2 times x2 modulo 5 times 7 is a solution to our system here. Can you see why? This is actually obvious because in this case, if we work modulo 5, we will get that this is congruent to 3 times x1 plus 2 times x2 modulo 5, and actually x1 modulo 5 is 1, so we get here that this is 3 times 1 modulo 5, and this is because we have x1 congruent to 1 modulo 5, and plus 2 times 0 modulo 5, and this is because x2 is actually congruent to 0 modulo 5, and from this we will get that this is congruent to 3 modulo 5, which means that our x here, combination of x1 and x2, is a solution to our first equation. The same thing happens actually modulo 7, and this is because this number that we have here, modulo 7, x1 is congruent to 0, so we get rid of the 3, and x2 is congruent to 1 modulo 7, which keeps us a remainder 2 modulo 7. And this is actually our second equation. So what we're going to do here is instead of solving this system, we're going to solve both of these and get the general solution x. Actually, this might seem to you less efficient than our first method because instead of solving one system, we're going to solve two systems, but for more than two equations, this method here is way more efficient than the first one. Off we go. The second equation of our first system here means that x1 is a multiple of 7, so one could write x1 as 7 times a certain integer m, and our second equation means that this is congruent to 1 modulo 5, which means actually that 7m minus 5 times a certain integer n, we can actually put a plus here, is equal to 1. Now if we solve this for m and n, one can deduce easily x1, which is 7 times m. Things are quite the same actually for the second system because the first one here says that x2 is a multiple of 5, and actually we can write x2 as 5 times a certain integer n, which will be equivalent or congruent if you would like to 1 modulo 7, and this means actually that 5n plus 7 times a certain integer m is equal to 1, and if you solve this, which is the same actually equation here, one can deduce the value of x2. From what we've seen previously, m actually is of the form minus 2 plus 5t, and you can check by yourself that n will be of the form 3 minus 7t, for of course the same integer t here. From here we deduce that x1, which is equal to 7m, is equal to 7 times minus 2 plus 5t, which is equal to minus 14 plus 35t. This means that the solution of this system here is x1 congruent to minus 14 modulo 35, and minus 14 modulo 35 is the same thing as as 21 modulo 35. Now from here we get that x2, which is equal to 5n, should be of the form 5 times 3 minus 7t, and this is because n is of the form 3 minus 7t, and this gives us 15 minus 35t. This means actually that the solutions of this system are of the form x2 congruent to 15 modulo 35. Now that we solved both of these equations, the solution to the first system is rather easy to deduce from what we've seen before, and actually we should have x congruent to 3 times x1, and x1 is 21, so 3 times 21 plus 2, this 2 that we have here, times 15 all modulo 35. So this would give us 3 times 21 is 63, and 2 times 15 modulo 35 is the same thing as minus 5 modulo 35, and we get here x is congruent to 58 modulo 35, and we know that 58 modulo 35 is the same thing as 23 modulo 35. Bingo! This is actually the same solution that we found together with our first method. Now the big question is, this method here generates the solutions to the system x congruent to 3 modulo 5 and x congruent to 2 modulo 7, but nothing says here that we found all of the solutions, right? Nothing proves actually that all of the solutions are of the form x congruent to 23 modulo 35. And thankfully, the Chinese remainder theorem that we will prove later on will help us prove that this method gives us all the solutions to our system. The Chinese remainder theorem says as well on what conditions such a system can have a solution. Actually, not all the systems are solvable, and for instance, the system x is congruent to 1 modulo 2 and x is congruent to 4 modulo 6 cannot have a solution, and this is because if x is congruent to 4 modulo 6, then x is congruent to 4 modulo 2 because 2 divides 6, and this means that actually x is congruent to 0 modulo 2, and one knows that x cannot be congruent at the same time to 1 modulo 2, meaning it is an odd number and be an even number at the same time, right? So this system cannot have solutions. We will see that the Chinese remainder theorem will give us an answer to the general case. Let us now move on to a problem that will yield a system of 3 equations. This problem actually was solved by the Chinese mathematician Sun Zi in the 4th century. We have certain number of horses, lesser than 100, and we would like to count them. Instead of counting them naively, we will order the horses by 3, and there will be 1 remaining horse. When we order these horses by 5 and 7, there remains each time 3 horses on their own. Now the problem is to find the number of horses. If we denote x the number of horses, this problem is actually equivalent to solving the system x is congruent to 1 modulo 3, x is congruent to 3 modulo 5, and x is congruent to 3 modulo 7. In order to solve this, we will solve 3 systems, which will be simpler, namely, x is congruent to 1 modulo 3, I'll denote this x1, sorry, x1 is congruent to 0 modulo 5, and x1 is congruent to 0 modulo 7. The second system will be x2 is congruent to 0 modulo 3, x2 congruent to 1 modulo 5, and x2 is congruent to 0 modulo 7. And the third and final system will be x3 congruent to 0 modulo 3, x3 congruent to 0 modulo 5, but x3 will be congruent to 1 modulo 7. Now, if we can solve this system, I claim that the number x, which will be congruent to 1 times x1, this x1 here, plus 3 times x2, this x2 here, and this 3 here, of course, plus 3 times x3, modulo 105, 105 is 3 times 5 times 7, will be a solution to our system here. Once we have our number here, we will find the number of horses. This first system is easy to solve because both of these equations imply that x1 should be of the form 35 times a certain integer k1, and this is because 5 and 7 are coprime. So if 5 divides x1 and 7 divides x1 too, then 5 times 7 must divide x1, namely 35 divides x1. The first equation here implies that 35k1 must be congruent to 1 modulo 3. But if we reduce now 35 35 modulo 3. 35 is actually the same thing as 2 modulo 3, so we get 2k1 is congruent to 1 modulo 3. From here, actually, if we multiply both sides by 2, we get 2 times 2 times k1 is congruent to 2 modulo 3, and actually 2 times 2 would be 4, and 4 modulo 3 is the same thing as 1, so we get that k1 is congruent to 2 modulo 3. Very nice. This means actually that x1 is of the form 35 times k1, but k1 is of the form 2 plus 3 times n1, so we get here 2 plus 3, a certain integer n1, and we get 70 modulo 105. So x1 is of the form 70 modulo 105. For x2 here, we see that x2 is a multiple of 7 times 3, which is 21, so x2 is of the form 21 times k2, which is congruent to 1 modulo 5, so we get here that 21k2 is congruent to 1 modulo 5, but if we reduce 21 modulo 5, we get that 21 is congruent to 1 modulo 5, so we get that k2 will be congruent to 1 modulo 5. This means actually that x2 is of the form 21 times k2, and k2 is of the form 1 plus 5 and 2, and this actually yields something congruent to 21 modulo 105, because 21 times 5 is 105. Same thing actually happens for x3. x3 is a multiple of 15, so it is written as x3 equals to 15k3, which will be congruent to 1 modulo 7. But modulo 7, 15 actually is the same thing as 1, so we get that k3 is congruent to 1 modulo 7, and this actually gives us that x3 is congruent to 15 modulo 105. Bingo! Now if you get back to this, we know that x must be congruent to 1 times x1, which is 70, plus 3 times x2, x2 is 21, so 3 times 21 is 63, plus 3 times x3, and x3 is 15, so this gives us 45 modulo 105, and if you reduce these modulo 105, one gets that the solution is 73 modulo 105. Bingo! Actually, because we know that the number of horses is lesser than 100, we know that the solution, meaning the number of horses, is equal to 73. And you could check by yourself that 73 is congruent to 1 modulo 3, and this is because actually 72 is divisible by 3. It is obviously congruent to 3 modulo 5, and it is also obviously congruent to 3 modulo 7. And because there is only one solution lesser than 105, we know that the number of horses is 73. Our exciting lecture ends here, and we will investigate in future lectures the Chinese remainder theorem. Thank you for listening.